start. So, in this class, what I'll do is that I will be discussing the these questions for related to the things which we discussed in the last week. Because what happens is that in the present week, the assignment questions consist of the starter methods. Okay, so what I'll do is I'll first discuss the questions. Questions are very simple, and then I will discuss some theory related to braking. Okay, there is some equivalent circuit diagram for the braking and all, which I'll continue in the next class along with the single phase machine. Okay. So single phase motor questions you will find in the maybe in your next assignment. So I'll discuss it when I'm discussing the next assignment. Okay. So let me then just start here. So let us first discuss the questions. So what I'll do is I'll parallelly open the last assignment theory, because in the last assignment we saw the relations of various starting methods with the direct online starting methods, right? The relation between the starting currents, the ratios of the starting currents, the ratios of the starting torques. Okay, so I'll keep that last assignment which I discussed open, so that we can come back here and see the things, okay, depending on the question. So let me just first discuss the questions. So here, this is your first question. So in this first question, what is it? It says is that, so let me just hide this, hide, okay. So here, in this first question, they have given you some common data. So in this data, they are saying that this is a three-phase squirrel cage induction motor with 450 volt line to line AC voltage. Then 12 kilowatt is the output power. Remember that whenever the power is mentioned with the motor, it means the output power. Okay. So whenever in any question, not only in this assignment, in previous assignments also, you will see that we sometimes use the output power information, right? So whenever in any question you see the power being mentioned, it is the output power of the motor. Okay, so this you have to remember not only in this question, for other questions also. Okay, so they have given you the output power and the line to line voltage rating of the motor. Then they are saying this motor has an efficiency of 88% and power fact, and it is operating at power factor of zero point 0.8. Okay. Now they are saying various things, that the motor is supposed to be delta connected during the full load operation. Remember that in the last class when we discussed the star delta operation, what we do is, for reducing the starting current, we first connect the machine in star, and then by using the switching arrangement, we change the connection to delta. So in the other starting methods also, when we were discussing, for comparing it with the star delta case, we considered that the machine under normal operation is connected in delta. That is why in this question also they are saying that, okay, this connection is delta connected. So in case there is some star delta question, it is logical. Okay, that is why they are saying that this motor is supposed to be delta connected during the full load operation. Now they are saying also that the starting current at the rated voltage is 6 times the full load current. So these are the things which are mentioned. So I'm just writing this, that I starting is 6 times of I full load. Now they are asking you to estimate the line current in ampere drawn from the supply mains at starting if direct online starting is used. Now direct online starting means you're not using any starting methods. So whatever is the usual process of calculating the input current, that is the process which you will follow. So so what is the relation so first of all, because we are interested in calculating the starting current, so starting current means the current which is getting input to the motor. So this is your motor. So because they have said it is delta connected, so I'll, instead of connecting it in star, I'll connect it delta. So this is the stator of your motor. Okay, so see, for motor, the current which is getting drawn corresponds to the input power, right? Because the output of the motor is mechanical power and the input is the electrical power. So because we are interested in calculating the starting current which is getting drawn, so we have to relate it to the input power. Okay, so for this what you will do is you will use the relation between the output and input by efficiency. So output power is given as 12 kilowatt here, so this is 12 kilowatt by input power is equal to how much efficiency? 88%. So I'm writing it in fraction. So it becomes 0.88. So what is input power? Input power is 12 kilowatt by 0.88. Okay. So this is the thing. Now you see another thing is that they are saying that this machine is operating at zero point 0.8 power factor. So if you will see, so what is the relation between the power factor and the active power? So first of all, you can because this is a three-phase machine. So what will be the three-phase power? It will be 3 V phase I phase cosine of the angle difference between the phase voltage and the phase current. Okay, so this is your power, in this case input power. Now so here so this phase voltage and the line to line voltage for the delta connection is same. So V line to line voltage is V phase. Okay, so you see but here the phase current is how much of the line current. So for delta connected system, phase voltage is equal to phase voltage is equal to line voltage, and phase current is equal to line current by root 3. Now remember that uh, it is asking you to estimate the line current drawn. Okay, so in this power expression you have to replace this phase current by the line current. So what I'll do, I'll instead of phase current I'll write it as line current by root 3. And I am writing it as cos phi only because it is known that this power factor angle is the angle between the phase voltage and the phase current. Okay, this is the input power. So what do you have? You have root 3 VL IL, because V phase is equal to line voltage, so I am replacing V phase by VL. IL cos phi is equal to input power. So what will be your rated current? Because remember that this power and everything, this is for the rated condition. Okay. So this 12 kilowatt output power is the output power at rated at full load. Okay. So that is why whatever we are calculating the things at rated value or full load. Okay. So what will be the line current then? Line current will be input power by root 3 into VL into cos phi. So you have input power from here. So input power is 12 kilowatt by zero point 0.8 into root 3 into VL. VL is given as 450 volt line to line. So I am using that 450 volt. 450. So this is 4 into cos phi. What is cos phi? 0.8. So using this, you can calculate. So your full load line current will come out to be 21.869. Why this is full load current? Why this is full load line current? Because the power, output power, which is mentioned in the question, this 12 kilowatt, right, which we took for by using the efficiency, we used it to find the input power. This 12 kilowatt power is the power at full load. So it is the output power of motor. So I'll finish this at full load. Okay, so in every question, whenever you see that the power is mentioned, that is the output power, but it is the output power at which load? It is the output power at full load. Okay, so that because we use the information of output power at full load, we from using that information, we were able to calculate the line current at full load. So line current at full load is 21.869 ampere if you calculate. So this is the full load line current. Now in the question, what they have said They have said that the starting current, so you read this statement here. They have said that the starting current at rated voltage is 6 times the full load current. So starting current is 6 times the full load current. Okay, so this is full load. So this will be how much? 6 into 21.869, which will give you this 131.2159. Okay. Is this question clear? Okay. It's very simple only. You will find that this assignment is quite simple and not very calculation intensive also. You can do it easily. Okay. Just you have to remember the starting methods and what is the how much factor. Suppose let us talk about the star delta starter. So in the star delta starter, the starting current becomes one third of the direct online starting current, right? Like that, and starting torque becomes one third of the starting torque in direct online starting method. So you have to remember this one third x square and all that thing. If you remember that, then this assignment is very simple. Okay, very simple, I must say. So now they're asking you that if suppose estimate the line current drawn from the supply mains. So first of all, from the previous question, the starting current which we found out for this machine is how much? It is starting current for this machine is 21.869. 21.869 into 6, because 6 times the rated value, so it was how much? It is 131.21. Okay, so this is 131.21 amperes. Okay. Now they're saying that if suppose you use the if you use the if you use the starting method using auto transformer starting method, then what will happen to the current which is drawn from the supply mains if the tapping, if the x where x is tapping is 55%. Okay, so let us go to the previous class. So let us see what is the relation between the starting current drawn by the auto transformer and the on direct online starting current. Okay, so let us go to the auto transformer method. So this is reactor, this is the auto transformer starting. Now you see in the auto transformer starting, so here you see we when we took the tapping at x percentage, so this x is the percentage of the tapping. Okay, for the auto transformer which will be mentioned in the question. So if your tapping is at x percentage, then you see the starting current drawn by the auto transformer is x square times the starting current drawn by the online starting method. So you can see this, so that you can see here that it is x square times. So the starting current, which line current which will be drawn here by the auto transformer, it will be x square times the starting current if you do not use any starting method. So we saw that if we do not use any starting method, so our current starting current drawn is this much. So what will be the starting current if we use auto transformer? So starting current drawn by auto transformer is x square times starting current drawn by direct online starting. Okay, so this was the IDOL start. So this is x square times IDOL start. So x is mentioned as 55%, or in fraction it is 0.55. So I starting auto transformer is x square times I starting DOL. So x is 0.55. So you take 0.55 square into IDOL. So IDOL we calculated in the previous question, which is 131.21. So if you do that, you see the current becomes so less, 39.692 ampere. So you saw that the if you do not use any methods, so we can see that the starting current is so huge, right? 131.21 ampere. It will definitely burn the windings if you do not use any starting method. That is why if you use the auto transformer starting, then you can see that the current is reduced by such a value, right? By so much it has reduced. So that is why you need to use starting methods for induction motor. Okay. So now we go to the next question. Now in the next question they're asking you what will be the line current drawn if star delta starter is used. Okay. So now let us go to the last assignment. So let us see what will be the line current drawn by the star delta starter. So this is the star delta starting. So here in the star delta starting when we discussed, so if you see here, you can see that the starting current drawn by the star delta starter and if you take the ratio of the starting current drawn by the star delta starter to starting current drawn by the direct online starting, you will see it is one third. So the starting current by the star delta starter is one third of the starting current by using dual. Okay, so that is why in this question what you will do is you will just simply do, so we will use this relation that I starting star delta is one third I starting DOL. You will just simply use this. So I starting DOL we had from the first question, which is this 131.2159. So you will take this 131.2159 and you just simply take one third of this value. So you will get 43.7. If you do this, you will get 43.73 amps. Okay. So is these things is these three questions clear? These three questions were very simple, as you can see. Just you have to remember the relations between the various starting methods. So is question clear, Abhitej? Is this question clear? Uh, uh, hmm, yes. So. Hmm. Yes, yes. So what you will have is you will have some switch arrangements like this. So I think sir has drawn that switch arrangements. It's okay. So some machines come with that switching arrangements. So you will have some switches here which will maybe change the. So you can have that. Okay, you can just see that it is a bit little bit complex to draw it just like that. Okay. Um, you see what happens is that in the star and in the star connection the current phase current is same as the line current. Okay. Huh. Yes, actually, most importantly, if you see here, let us go to star delta starting methods. So if you see that, so you will see that the calculation of this starting current is highly dependent on the phase voltage. Okay, on the phase voltage if you see, because when we draw the equivalent circuit diagram we use the per phase voltage. So you will see that in the when we connect it in the star in the beginning, the phase voltage is reduced by root 3 times. Because this phase voltage is reduced by root 3 times, automatically the current is also getting reduced by root 3 times. Okay, like that. And you will see that, but when you bring back the delta connection, now in the delta connection this will be if you select, if I do yes, voltage will be same. So by that what you are ensuring is that you have the less starting current in the beginning. Okay. 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 Hmm. Okay. So maybe these kind of methods could be used there also. Depends on the equivalent circuit diagram. I think this can be extended there also. I think it should not be a problem. Okay. Yes. Hmm. And consume. Hmm. Yes, yes. Hmm. Actually, if you if in our undergraduate labs, I remember that we had the star delta starter. So there they have some, what you say, commercial switching. They have the laboratory prototype where they had this commercial switching arrangement. So by just pressing that switch, what used to happen was that the connection used to change. So so maybe. Um, Actually, I don't know because see, my BTech college and this college is different, so I don't know whether here they have this experiment or not. I don't think they have this experiment. They do other sides of experiments here. Okay. Huh. But I think that that is a very very standard thing. I think you can find it in the net also. I believe. Okay. Okay. So as such, as coming to the questions are very simple. I guess we just have to remember this. Okay. Now, so now let us go to the next set of questions. Now, in the next set of questions, what they are saying is that a three-phase squirrel cage induction motor has per phase rotor resistance of 0.08 ohms, per phase rotor reactance of zero point 0.8 ohms, and then they are saying to neglect the stator impedance and negligible no load current. So you know that we have to go to that equivalent circuit diagram, which is the simplified one, where you are just having the where you're neglecting the rotor stator parameters and you only have the rotor parameters, right? So we are referring to that circuit diagram. Like last assignment and even the before that assignment, we took that simplified equivalent circuit, if you remember. So here now they are asking that if suppose you use the direct online starting is whatever we have discussed till now. Okay, all the things which we have discussed, all the equations which we have arrived at, they all relate to direct online starting. Okay, so what you will do is first you will find the things for the direct online starting, and then by using these ratios you will relate it to the other starting methods. Okay, that is the context of this assignment here today. So here if you see, they are saying that if you use the direct online starting, then estimate the ratio of the starting torque to T max. Okay. So first of all, we know that torque at any slip S is equal to Ks alpha by S square plus alpha square. We have seen it so many times. And Te max is how much? K by 2. So T it's any slip S and T max, if you take this ratio, you will get 2S alpha by S square plus alpha square. Now they are saying that the starting torque. So we know that for the starting torque, slip is equal to 1, okay, for starting, divided by T max. So here what you have to do is instead of wherever this S is there, you have to replace it with 1. So this becomes 2 alpha plus, but divided by 1 plus alpha square. Now what is alpha? We know that alpha is the slip at which the maximum torque occurs. Slip at which T max occurs. And for simplified diagram, it is not as from the maximum power point, this maximum power theorem, you can find that it is nothing but your R2 dash by X2 dash. So what is your R2 dash in the question? It is 0.08 ohms and X2 dash is 0.8 ohms. This we have discussed so many times. This we are discussing from the last two assignments. Okay. So there should be no confusion in this. So we have obtained this alpha. So alpha is zero point 0.1. So you have this starting torque to T max. So it is just 2 into zero point 0.1 by 1 plus zero point 0.1 square. So this is zero point 0.2 by 1.01. So this is the what you say ratio. So if you do that, you will get this as 0.198. So this is 0.198. So the ratio of the starting torque to the maximum torque under normal condition where you are not using any starting methods, which is the direct online starting. So the ratio comes out to be 0.198, which we have seen. We have discussed this so many times. Okay. So this was a very simple question. Now if we suppose use the star delta starting, then what will be the ratio of the starting torque to the T max? So let us see what happens to the torque when we use the star delta starter. Okay. So you see in the last class when we discussed that when we use the star delta starter, so starting torque also reduces, which we do not want though, but it happens. Okay. So the starting torque becomes 1/3 of the starting torque of direct online starting method. So whatever starting torque ratio which we have obtained, we just have to divide it by 3. Okay. So, okay. So T starting, so we will write like this. So T starting star delta is 1/3 of T starting DOL. So in the last question, we found T starting DOL by T max as 0.198. Okay. Now they're asking you what will be T starting star delta by T max. This ratio they're asking you now. Okay. By this ratio, they mean that. So in place of T starting DOL, you just replace this, what you say, this relation. Okay. So from here, what you get that T starting DOL is 3 times of T starting star delta. So this T starting in the place of T starting DOL, you just replace this 3 times of T starting D delta. So this becomes 3 times of T starting star delta by T max as 0.198. Okay. Now what will be T starting star delta by T max? So if you cross multiply, you just bring this down. So this becomes 0.198 by 3. So this comes out to be 0.066. Okay. So is this question clear? What all things we did? This is very simple though, but if there is any doubt, please ask. There is any doubt here? Huh. Now they are saying that if you use the auto transformer starting with 65%, huh. So so here you see, if we use direct online starting, then when we estimated we use this value because this is direct online starting, right? So that is what we are comparing it with. Okay. So then again, they're asking that if suppose we use auto transformer starting with 65% tapping, then what will be the ratio of starting torque to T max? Okay. So now X is 0.65 for the auto transformer method. So if you go back, so let us see what is the what is the relation between the torque of the auto transformer starting method with direct online starting. So you see torque of this auto transformer starting here is x square times of the starting torque of DOL. Okay. So what you will do is that, so let us now do this. So ultimately what we want, you want T starting auto transformer by T max. This ratio we have to find. Now what we know T starting DOL by T max. So T starting DOL we know from the first question, which is 0.198, this ratio of T starting DOL to T max. So we are taking this 0.198. Okay. Now this T starting auto transformer, how it is related to T starting DOL? It is x square times T starting DOL. So what about T starting DOL? It is how much? It is T starting auto transformer by x square. So here we will replace this T starting DOL in this equation by T starting auto transformer by x square. So which will give you T starting auto transformer by T max, and then there is 1 by x square is 0.198. So T starting auto transformer by T max x square into 0.198. Okay. So what is this x? X is 0.65. So here it is 0.65 square into 0.198. So if you do this, you will get this value. Okay. So this is the value which you will get. Okay. This is also simple only. Just have to remember that T starting auto transformer is x square times of T starting DOL. Okay. This is the only thing which we need to remember. So this is clear, right? Abhitej or another Nitin is if there is doubt, please ask. Okay. Now we are going to the next question. Now in this next question, they are saying, so you have to read these three statements very carefully. They are saying that the full load current is 19% of the starting current. Full load torque, so I'm just writing that full load torque is 70% of the T starting. T starting basically T starting DOL, because if you do not use any methods, okay, then that is the thing. So wherever which they are giving you this ratios, suppose I full load is 19% of I starting DOL. Okay, so these things is all DOL. Okay, by default, because there is no starting methods uh, given in this data. Okay. So now they're saying that if suppose this auto transformer method is used, uh, so that we get the, so they're saying that now what you want is you want so T auto transformer is such that it is T full load. Okay, so they're saying that the auto transformer is connected in such a way, auto transformer starting is used such that we get full load torque at starting. So they're saying that by using the auto transformer method, T starting auto transformer is T full load. Okay, so what is this T starting auto transformer and what is this T full load? It is 70% of the T starting DOL. Right. Now they're asking what should be the tap ratio of the auto transformer at starting. So we know what is the relation between T starting auto transformer to T starting DOL. So what it is? It is T starting auto transformer is x square times T starting DOL. Okay. So just if you compare these two equations, equation 1 and equation 2, then you can just see that x square is equal to 0.7. Okay, so this x square is 0.7. So what is the percentage of tapping? So this comes out to be 0.836. So in percentage, it is 83.6%. Okay, so is this question clear? This question is little bit tricky. Try to understand it. So is there any doubt? Should I repeat it again? This for you it is clear, right? Because it just so what they're saying is that the auto transformer, you are using the auto transformer starting. Now when you use the auto transformer starting, So what they're saying, it is such that you get full load torque. Now remember that the full load torque is 70% of the starting torque of DOL. So what you're doing, that then if you if you replace this full load torque as 70% of the starting torque by using DOL, direct online starting, so you will see that auto transformer starting torque should be 0.7 times of starting torque of DOL. We know that auto transformer starting torque is x square times of starting torque of DOL. So if you compare these two equations, the x square is equal to 0.7, which will give you the percentage of tapping. Okay. So now we go to the next question. Now in the next question, they are saying that estimate the line current drawn by the motor from the auto transformer at starting. Okay. So first of all, what you will do by using this power, we know that this output power which is mentioned is full load output power. So if we use this full load output power, so if we use this full load output power and power factor and all that, what you will get is you will get full load line current. So let us do this then. So output by input is efficiency. So input is output by efficiency. This is output is given as 20 kilowatt, by efficiency is how much? 75%. Okay. And what is input power equal to? Input power is equal to root 3 VL IL cos phi. Okay. IL full load, because power is full load power. So line current which we are getting is full load line current. Okay. So so here now we will replace the things which we know. So we know that we line to line voltage is 380 volt. Here in this question, this is 380 volt. So root 3 into 380 into I full load, and cos phi is given as 0.74. So this is 0.74. So this will give you the I full load current, line current, which is 54.75 ampere. Okay. Now you see, we know, now you know that first of all, we calculated the full load current, but what is the relation between the full load current and the starting current? So starting current DOL, because if you do not use any methods, we are not using any method till now, right? In all this calculation, it is DOL. Okay. So starting current DOL is full load current by 0.19. So this will give you 288.163 ampere. So starting current of DOL is 288.163 ampere. Now they're saying estimate the line current drawn by the motor from the auto transformer at starting. Okay. So now let us go to the auto transformer method and see what is the relation between the starting current of auto transformer to the starting current of DOL. Because from all this, first of all, we found the full load line current, and in the question, full load ratio of full load line current was given and starting current was given. So from that ratio, we use the full load line current information to get the starting current, and the starting current is starting current DOL, because no method is used in this equation, in these relations. So this is starting current direct online. Okay, direct online starting. Now what we need is, we have to use the, now because we know the starting current of DOL. Now we can use it by using the percent. We know if we know the tapping of the auto transformer, then we can get what is the line current drawn by the auto transformer. So let us see the previous assignment. So in this previous assignment, you see there are two places from which it is drawing the line current. One is the line current which is drawn by the auto transformer here from the actual line, and there is one line current which is drawn by the machine or the motor. So there are two places where the line current is drawn. Now the line current drawn by the machine, if you see, so line current drawn by the machine, so I'm just writing here. So okay, so I'll just use a different color. So in this whole discussion, if you will just go back, you will see that I starting line current machine is x times of I starting line current DOL, and I starting line current auto transformer is x square times I starting line current DOL. So here the line current which is drawn is x square times, but here the line current which is drawn is x times. Okay, so I'm writing these things there also again. Okay, so coming to this question. So I starting line current machine is x times of I starting line current DOL, and I starting line current auto transformer is x square times I starting DOL. Okay, this is important. Now you see what they are saying. They are saying estimate the line current drawn by motor or machine. Okay, they're not saying line current drawn by the auto transformer. They're saying line current drawn by the machine. So what should be I starting line current motor or machine? So it is motor or machine is x times of I starting line current DOL from this expression. Okay, so now we know x also. We have calculated x in the previous question as 0.836. Okay, so this x we will just use here. So we have 0.836 and you have I starting DOL which is 288.163. Okay, so if you do that, you will get this as 241.095 amps. Okay, so this is what will be the line current drawn in the motor side. So this question is clear. Hmm. Now, just now they're asking for the same auto transformer method, estimate the line current drawn from the supply mains by the auto transformer. Now we know that I starting line current drawn by auto transformer is x square times of I starting line current DOL. From this above relation here that I starting line current auto transformer is x square times I starting DOL. So this will be nothing but x we know from the previous to previous question as 0.836 which we calculated. So this will be 0.836 square into I starting DOL which we calculated in the last question. So in the last question I starting DOL was 288.163. So this is 288.163. So this will give you 201.74 amperes. Okay. So this is the starting current which is drawn by the auto transformer from the actual supply. Okay. Which is x square times of the starting current of DOL. And x value we obtained from this question, seventh question here, and the I starting DOL we obtained in this calculation. Okay. Now they're asking you that estimate the line current that would be drawn from the supply if we use the direct online starting. So whatever actual things which we calculated, this calculation which we did, like first we found the full load current by using this output by input efficiency thing. Okay, we calculated the full load current, and in this relation, this full load current to starting current, this relation if you see here, in this relation here. So in this relation, because there is no starting methods used, so when we use this relation to get the starting current, we obtain starting current DOL only. So when you obtain this, we already know the starting current DOL is 288.163. So they are just saying this is starting current DOL, which is 288.163. Okay, which we just calculated in question 8. Okay, so this is 288.163. Okay, so you can see that this assignment is very simple, right? Like it's not very tricky. It's all things are very simple, straightforward. So is there any doubt in all the questions which I discussed right now? Very clear, right? Now in your present assignment, all these kind of questions are only there, right? Not related to braking or the single phase induction motor. These questions only, right? Okay, okay, okay. Okay. I think it will be almost same because in most of the assignments we have seen that the pattern is same, right? Similar questions are followed. Okay. So uh, yes, yes. They are same. The pattern is same. Same. Okay. So now I'll just discuss the breaking and then I'll continue the discussion of the breaking in the next class. Okay. Um, or maybe what should I do? Should I maybe, because we will be having the breaking questions, so maybe I'll discuss the breaking itself in the next class only so that it is continuous. Huh. Okay, it should not be a problem because we saw, right, that the starting method I discussed in the last class, but we are doing it now, so I have to again go back and again. So I think it next week only so that it is continuous. Yes, yes. So I think that is what I'll do. Okay, so I think that is it for the this class, and if there is any there is no more doubt, then I'm stopping the class today here. Okay. 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 So is there any doubt for the other Nitin? Is there any doubt for you? If there is any doubt, please ask. Okay. So I think if there is no doubt, then I'm stopping the class here. So that is it. I'm stopping. Okay, we can leave. I am also leaving. Okay. Okay then. So I'm stopping the class here.